So for perfect square trinomials, there'll be two parts to this question. The first part, they'll ask you if the polynomial is a perfect square trinomial. So looking at the first example here, we have x squared. It says the first and last terms are perfect squares. So x squared is x times x, so that's a perfect square. Or the square root of x squared is x. The square root of 4 is 2, or it'd be 2 times 2 to get to 4. And then the middle term has to be 2 times, let me get a new color, 2 times this x, one of those factors, and one of these factors, so the 2 there. So 2 times x times 2, which is 4x. So this is a perfect square trinomial, and then to factor it, you take the variable from the first term, and the number from the second term, and we use the sign that's in front of the b, or the first operation. And then that would be squared. X plus 2 in parentheses squared, and you can check your work with FOIL. So to see if this polynomial is a perfect square trinomial, I'm looking at the first and last terms again. The first term is a perfect square because it's x times x, and 49 is 7 times 7. And then we're going to take, for the middle, always 2, twice the first term, and the second term square rooted. And 2 times x times 7 is 14x. So this is a perfect square trinomial. And then I can factor it. I take the square root of the first term. We use the sign, the first operation that shows up, or the sign before b. And then our last term square rooted, squared. So x minus 7 squared. Okay, our last one, to determine if this is a perfect square trinomial. Again, I'm looking at the first and last term. The first term is 9x squared, so it breaks down to 3x times 3x, so that is a perfect square. 4 is 2 times 2, and in the middle we would have 2 times 3x times 2, which is 12x. So this is a no, not a perfect square, and so we cannot factor it. We stop there. To determine if something is a difference of two squares, there's conditions that apply as well. We need to have a binomial, we need to have subtraction, and we need to have perfect squares in the first and last term. So looking at this first example, 1 minus 4x squared, we have subtraction, it is a binomial, and the first and last terms are perfect squares because 1 would be 1 times 1, and 4x squared is 2x times 2x. So the way we write our final answer then, since it is we would write yes, and then we're going to have two binomials with different signs. So think difference of two squares is going to have different signs. And so we put the first term of 1 and the next term square root of 2x, and we do the same thing for the second binomial. Next example, p to the 8th minus 49q to the 6th. Any even exponent is going to be a perfect square. So if I take the square root of p to the 8th, I'm going to get p to the 4th times p to the 4th, or the square root is just p to the 4th. And for the last term, we have 7q to the 3rd. Because if you multiply that, 7q to the 3rd times 7q to the 3rd, remember that we keep the base and add the power, so we get 49q to the 6th. Now, to make sure that was a difference of two squares, we have a binomial, we have subtraction, and those are both perfect squares. Both terms are perfect squares. So our final answer is going to be yes. And then we have two binomials with different signs. And then we write our p to the 4th and our 7q to the 3rd. And for the last problem, 16x squared minus 4y to the 5th. We have a binomial, we have subtraction, but both terms are not perfect squares. This last one is not a perfect square because it's y to the 5th, and any odd powers cannot be split. You can't take a square root of y to the 5th.